Hello and welcome to Data Science for Everyone. Today we're going to learn about A/B testing. A/B testing is a method used to make informed decisions by comparing outcomes across two conditions in a controlled experiment. For example, A/B testing can help improve user experience on a website or evaluate effectiveness of training methods. In this video, we will walk through analyzing A/B test data to support decision making and predictions. In today's video, I'll discuss the concepts of A/B testing, how to set up null and alternative hypotheses, determine sample sizes, and I'll discuss how to perform power analysis. I will be covering t-test, Mann-Whitney U test, chi-square test, Fisher's exact test, Pearson and Spearman correlations. Regression is also a part of A/B testing, which I've covered in a different video. I have linked it in the description. Before I start, I'd like to request that if you love my videos, please like, comment and subscribe to my channel. Let's say we want to find out whether people solved word puzzles faster than logic puzzles. We use a between subjects design, meaning each person attempts only one type of puzzle. Participants are randomly assigned to either Group A or Group B. Group A solves word puzzles and Group B solves logic puzzles. In our A/B design, Group A serves as the control group and Group B is the experimental group. This setup allows us to observe any differences in solving time due to the puzzle type. Let's look at the data collected from the game. As you can see, the data contains three columns. The first one is the puzzle type column, which contains either word or logic, referring to word puzzles or logic puzzles respectively. The second column is called time to solve, which contains the time to solve for each puzzle in minutes. And the third column is experience rating, where the players has rated the game as one of neutral, fun and frustrating. Before analyzing the data, it is always good to explore the data visually. In a previous video, I've explained how to explore datasets and the link is in the description if you want to watch it. But for now, let's create a histogram showing how quickly people solved each type of puzzle. In this example, the histogram shows that participants in the logic puzzle group tended to finish more quickly than those in the word puzzle group. We can further break down the plots by puzzle type using the facet grid method in Seaborn. By the way, if you want to learn about how to plot using matplotlib and Seaborn, I have made detailed tutorials. The link is in the description below. So, what kind of questions can A/B testing answer? One kind compares group outcomes. For example, are logic puzzles solved faster than word puzzles? Another investigates relationships within the data, like whether greater interest in a puzzle is linked to solving it faster. These trends can be examined within a single group or across both groups. Group comparison questions test for differences, while relationship questions reveals pattern or differences between variables. A/B testing is most effective when there is a sufficient number of participants, adequate testing duration, and a clear hypothesis to execute the test properly. Some factors that can interfere with accuracy include sample variability, the number of variables in the study design, and natural shifts in behavior over time. Let's go over these key considerations to ensure reliable and valid A/B test results. A good A/B test requires sample that reflects a wider population. However, outside factors can shift outcomes. For example, people might solve puzzle differently on weekdays versus weekends, or during periods of high cognitive fatigue, like exam seasons. Similarly, public interest shaped by social media or news trends could temporarily influence performance. Ending the data collection during an unusually quiet or active time could bias the findings. Always be mindful of the timing and the context of data collection. We can see how results fluctuate just by looking at random subsets of the data. Let's take a look at 3 different random samples of 10 participants each from our puzzle dataset. Each sample may yield different average solve times, even though they are drawn from the same population. These shifts underline the importance of cautious interpretation, especially with small samples. It is also best to test one variable at a time. If we try comparing multiple variable combinations, say puzzle types that mix logic, math, and language clues, it becomes unclear which element is causing any observed effect. In contrast, a test comparing just word versus logic puzzles isolate the variables nicely. Multi-element tests confuse interpretation and often lack a proper control. The more variables or hypotheses you test, the greater the chance of type 1 error. A typical significance level alpha is 0.05, meaning there is a 5% chance of a false positive. If you conduct multiple tests, the chances of getting at least one false positive increases. For example, 10 tests at 5% significance leads to a 40% chance of at least one false positive. If you run 20 tests, the chances increase to about 64%. This is known as family-wise error rate. If you want to learn more about error rates, I have a couple of previous videos that explain them in detail. I have the video links in the description. Regression to the mean is another issue. Imagine that participants initially find logic puzzles easier just because they are novel. Over time, as novelty wears off, solve times may increase and align more with the average. If the test ends too early, we might falsely conclude that logic puzzles are always faster. That's why it's critical to include a stable control group to compare the changes against. Small sample sizes can also mislead. If one participant struggles with a word puzzle while others do fine, the average solve time may look high at first. But with more participants, the data becomes more stable and reflective of the true average. This reinforces the need for sufficient sample size in A/B testing. Power is a key concept in hypothesis testing. It refers to the probability of correctly rejecting the null hypothesis when it is actually false. That is, avoiding a type 2 error. For instance, suppose we believe that there is a difference in how long it takes to solve word puzzles versus logic puzzles. Power tells us how likely we are to detect that difference if it truly exists. High power means our test is more likely to reveal a real effect. Power is especially useful before collecting data. It helps us decide how large our sample size should be to confidently detect an effect. Without enough participants, a test might fail to detect a real difference, wasting time and resources. Power can also be assessed after a study to evaluate how reliable the findings are. With a smaller sample size, the sampling distribution is narrower. This makes it harder for test statistics to reach significance, requiring a bigger effect or a stronger test value. Today, we'll be using two packages for a statistical analysis: statsmodels and pingouin. To determine sample size, we'll use t-test-int power from statsmodels. First, we import t-test-int power method from the statsmodels package, and then we create an instance of the t-test-int power and assign it to a variable called analysis. To determine the right sample size for a meaningful experiment, we need three components: the estimated size, the desired power level, commonly 0.8, and the significance level alpha, which is typically 0.05. Plugging in these values, we see that the estimated sample size for this test needs to be 25. Effect size measures the strength of the difference we expect or observe. It is often calculated as the difference in means between the control and experimental groups. In our case, it is the mean time to solve word puzzles minus the mean time to solve logic puzzles. Before running a full study, effect sizes can be estimated using past research or pilot data. Afterward, they can be calculated directly from the collected results. Running a power analysis helps us assess the credibility of our results. If we know the sample size, the effect size and alpha, we can calculate power. For example, let's say we had 50 participants solving puzzles, an alpha of 0.05, and calculated an effect size of 0.8. We can compute the power of this one sample t-test using the power_t-test method from the pingouin package as demonstrated. Pingouin package is imported here as PG. This yields a power of approximately 0.98, indicating strong confidence in our test results. Power gives the probability that the alternative hypothesis is true if a significant difference is found between the groups. In our puzzle dataset, the distributions may end up similar and have no significant difference, indicating the groups derive from the same population distribution as seen on the left, or may be significantly different, indicating they derive from different distributions as seen on the right. One common method used in A/B testing is the independent sample t-test. T-tests check whether the difference between average values of two separate groups is statistically meaningful. For example, in our case, it tests whether there is a significant difference in how long people take to solve either word puzzles or logic puzzles. The null hypothesis assumes that there is no difference, and the alternative hypothesis assumes that there is a significant difference in the means. To use an independent t-test correctly, several assumptions must be met. The participants for the test must be randomly selected. The data should come from populations that are normally distributed. The two groups should have roughly equal variances. We can use a histogram to visually check for normality. If the distribution looks fairly symmetrical, we can assume normality holds true, which it does in this case. One of the standard methods to test normality in statistical analysis is the Shapiro-Wilk test. This test is particularly reliable for small to moderately sized samples, typically up to 5,000 observations. In Python, we can use the normality method in the pingouin package to run the Shapiro-Wilk test. The null hypothesis here is that the data is normally distributed. So, if the p-value is more than 0.05, we do not have enough evidence to say that the data is not normal. If the p-value is less than 0.05, it suggests that the data significantly deviates from a normal distribution. However, the test can be overly sensitive with large sample sizes. In those cases, even tiny deviations might appear statistically significant. That's why it is often complemented with visual inspection like histograms or QQ plots. In this slide, we apply the Shapiro-Wilk test to the two variables from a dataset for both word and logic puzzles, and the p-values are more than 0.05, which means that the data is normally distributed. We'll use the t-test int power from statsmodels to find out how many participants we need for our t-test. With an expected effect size of 0.7, power of 0.8, significance level of 0.05, and assuming a two-tailed test, we find that each group, word and logic, should have 33 participants. Setting alternative to two-sided means that we are not assuming in advance which group takes longer to solve the puzzles. Equal group variances are an assumption of the t-test. If the assumption is violated, it can increase the chances of false positive. We check this using the Levene's test using the homoscedasticity method from the pingouin package. A p-value above 0.05 suggests that the assumption holds and we can treat the variances as equal. As we can see, our p-value is 0.9, which is more than 0.05. It means that our data has equal variances. To perform the actual t-test, we use the t-test method from pingouin. We split our data into two groups, word and logic. We set alternative equals to two-sided to indicate we are not assuming that one group will be greater than the other. Since our variances are equal, we set correction equals to false. The result shows a p-value below 0.05. So we reject the null hypothesis and conclude that there is a statistically significant difference in the time it takes to solve the two puzzle types. We also get a 95% confidence interval for that difference. Cohens'd helps us understand how big that difference is. Here we have extracted the Cohens'd value from the t-test result. A value of 0.2 is small, 0.5 is medium, and 0.8 or higher is considered large. In this case, the effect size is 0.77, which is roughly 0.8, indicating a large effect size. We can compute the statistical power of our t-test using the t-test int power method from statsmodels package as demonstrated. A power of 0.8 or higher is typically considered acceptable, meaning that there is a 20% chance or less of a type 2 error, that is, failing to detect a real effect. In our case, the output shows a power of 1, which means our test is extremely well powered. It has almost zero probability of missing a true effect of the size we are testing for. With such a large sample and strong effect size, this test is highly reliable. Up until now, we have assumed that the data is normally distributed. What happens when the data is not normally distributed? In this case, we'll not be able to use a t-test, which is a parametric test. Instead, for data not normally distributed, we have to use a non-parametric test. The Mann-Whitney U test is a non-parametric alternative to independent sample t-test. While the Mann-Whitney U test doesn't assume a specific distribution, it does require that both groups to have similar shape distributions, whether both are bell-shaped, skewed, or something else. Unlike the t-test, which looks at the differences in means, the Mann-Whitney U test focuses on the medians. That's important because in non-normal distributions, the median gives more accurate picture than the mean. If our data were normally distributed, the t-test would be more powerful. But when normality is not present, the Mann-Whitney U test becomes a better choice. Its null hypothesis states that the medians of the two groups are equal. Again, we check the histogram to confirm both groups have similar but non-normal shapes to ensure that the Mann-Whitney U test is a better fit. Since the previous game data was normally distributed, this time we'll use a non-parametric data. The link to this dataset is in the description. We import the data and save it as game_data_np, and like before, we can plot the histogram to confirm that both groups have similar left skewed shapes, making the Mann-Whitney U test a better fit. Before running the Mann-Whitney U test, let's first determine the sample size for the test. We have two groups in our dataset. One is word and the other one is logic. This Python function calculates the sample size needed for a second group in a two-group comparison, given the sample size of the first group, which is n1. Since we fix the first group size, the code finds the second group size by trying different values until the designated power value. It does this using a numerical search method called bisection. Finally, it prints the required sample size for the second group, which in this case is n2. This helps researchers plan studies with uneven group sizes while maintaining statistical power. The output shows that for 100 participants in the word puzzle group, we need 97 participants in the logic puzzle group for an effect size of 0.4, significance level of 0.05, and a power of 0.8. If the number in the word puzzle group increases to 110, the logic puzzle group adjusts accordingly, though the total stays roughly the same. We run the Mann-Whitney U test using the MWU method from Penguin. First, we subset the two groups, word and logic, and use them inside the MWU method and save it in the results variable. Then we extract the p-value from the results variable. As you can see that the p-value is less than 0.05 and therefore our result is significant, meaning that there is a significant difference in the median time to solve the two types of puzzles. To interpret our results, we look at the effect size of the test. Effect sizes of 0.1, 0.3 and 0.5 are considered small, medium and large respectively. Our effect size is around 0.85, indicating a large effect. To find the test's power, we use normal int power from statsmodels. First, we create an instance of normal int power. Then we call the power method and input the effect size value of 0.85 to effect_size, set significance at 0.001, set 3000 participants to n1, and set the ratio of 1 to the ratio argument. The result shows a power of 1, which means our test is extremely well powered. It has almost zero probability of missing a true effect of the size we're testing for. With such a large sample size and strong effect size, this test is highly reliable. The chi-square test of independence is used when we want to see if there's a relationship between two categorical variables. Let's look at our puzzle dataset. Let's say after finishing, we asked each participant how they felt about their experience. Did they find the puzzles fun, neutral, or frustrating? So now we have two categorical variables: puzzle type, which is word or logic, and experience rating, which are fun, neutral, or frustrating. We can summarize this in a frequency table, a count of how many people in each group reported each type of experience. To generate a frequency table, we'll use the cross-table function from pandas. The null hypothesis of a chi-square test says that there is no relationship between puzzle type and how the participants felt about it. The alternative hypothesis says that the puzzle type and experience are related, that is, people's feelings depend on the puzzle type they solved. Keep in mind, this test won't tell us one puzzle causes a specific feeling, only whether there is a relationship between the two variables. To plan for this kind of test, we can estimate how many participants we need using the Goff chi-square power method from the statsmodels package. Like before, we need an effect size parameter. If the effect size is 0.1, it is considered small. If it is 0.3, it's considered medium, and for values of 0.5 or above, it is considered a large effect size. There is another argument called degrees of freedom, or DF, which is the product of the number of conditions in variable 1, -1, and the number of conditions in variable 2, -1. In our case, we have 2 puzzle types and 3 response categories, and we can calculate the degrees of freedom as 2 - 1 times 3 - 1, which is equals to 2. Using a small effect size value of 0.1, we can see that we need 784 participants for a well-powered test. Also, make sure that every combination in the frequency table has at least 5 participants for the test to be valid. To run the chi-square test, we're going to use the chi2 independence function from the pingouin package. We'll save it in the stats variable. We will be looking at the first row of the results. If the p-value is below 0.05, we reject the null hypothesis and say that there is likely a relationship between puzzle type and how people felt about the puzzle. In our case, the p-value is more than 0.05, and therefore we fail to reject the null hypothesis. This method works best with large sample sizes, typically over 1000, which makes this approximation more reliable. We also want to know how strong the relationship is. To do that, we can calculate the effect size, called Kramer's V, which is suitable for categorical data. In our case, we compute Kramer's V from the stats variable. The Kramer's V value comes out to be around 0.01, that suggests a very small effect size, meaning that there is little to no relationship between the two categorical variables. Finally, we calculate the power of our chi-square test using the power chi-square function from the pingouin package in Python. Given an effect size of 0.0126, a sample size of 6000, and a significance level of 0.01, the resulting power is only 0.03. This means that our test has just a 3% chance of detecting a true effect, which is very low. In practical terms, there is a high risk of a type 2 error. To improve power, we would either need a large sample size or a stronger effect size. Fisher's exact test is used when we are working with categorical data, things that can be grouped, like types of responses or preferences. It's especially useful when we have smaller sample sizes or when the expected frequencies in our data are very low. Let's say we are studying whether people's experience with puzzle, either word or logic, affects how they feel about it afterward. If the data is non-parametric in nature, with sample sizes under 1000, or some of the categories have very few observations, Fisher's exact test is often a better choice than chi-square test. This test is most commonly used for 2x2 tables, and while it can technically handle larger tables, the calculations can get intense. The key thing here is that Fisher's exact test calculates the exact p-value, not an approximation like the chi-square test. This makes it more accurate in small or uneven datasets. For Fisher's exact test, the null hypothesis states that there is no relationship between the type of puzzle and how people rate their experience. And the alternative hypothesis states that there is a relationship between the type of puzzle and the rating. To run the Fisher's test, first we build a 2x2 frequency table by running the crosstab function from pandas. Then we run the Fisher_exact function from scipy.stats package on the frequency table. If the p-value is less than 0.05, we can reject the null hypothesis. In our case, it is less than 0.05, which means that the puzzle type and ratings are related. Fisher's test also gives us an odds ratio, which tells us the size of the effect. Typically, an odds ratio of around 1.5 is considered a small effect, around 2.5 is considered medium, and 4 or higher is considered large. In our case, the odds ratio is 3.3. That means that participants were 3.3 times more likely to say that logic puzzle was fun compared to word puzzles. Finally, we use a power analysis to check whether we had enough data to trust our results. Using the normal int power class from the statsmodels library, we input the effect size, sample size per group, and significance level alpha. In this case, with an effect size of 3.28 and 800 participants per group, the computed power is 1. This means our test has more than enough power to detect an effect if it exists, making our results statistically reliable. Now let's look at correlation. A correlation assesses the strength and direction of the relationship between two variables, determining the amount of increase or decrease in one variable per unit increase or decrease in the other variable. A correlation coefficient is a numerical measure of correlation, meaning a statistical relationship between two variables. The value of correlation coefficient is always between -1 and +1. When the correlation coefficient is more than 0, it means that the variables are positively correlated, where an increase in x leads to an increase in y. When correlation coefficient is less than 0, it means that it has negative correlation, where an increase in x causes a decrease in y. And when the correlation coefficient is close to 0, it means that the variables are not correlated at all. Correlation doesn't mean causation. Here's a great example to demonstrate that. In this plot, we can see a strong correlation between ice cream sales and shark attacks over time. The correlation coefficient is 0.5 and it looks like they're closely linked. But of course, we know that eating ice cream doesn't cause shark attacks, or shark attacks don't make people buy more ice cream. What's really going on is a third factor, the season. Both ice cream sales and shark attacks go up during summer, so they move together, but not because one causes the other. This is a classic example of spurious correlation, and it's a reminder to always ask, is there a real causal connection, or is there something else driving both the variables? One of the most widely used methods to test significance of a correlation is called the Pearson correlation. It helps us understand how strongly two variables are related and in what direction. Before using Pearson's correlation, we need to make sure that the data meets certain assumptions. The first assumption is that there is a linear relationship between the two variables, and the second assumption is that the data must follow a normal distribution. Let's bring in the vitals dataset that contains the height and weight of several individuals. The data contains 3 columns: height, weight, and gender of 500 individuals. The link to this data is in the description. If we want to explore whether the heights and weights are related, we can run a Pearson's correlation test. If we analyze the data without considering the gender, our null hypothesis is that there is no correlation between the heights and the weights. But if we want to evaluate each gender separately, we'll test the same hypothesis within each gender group, male and female, requiring 2 separate hypotheses. To figure out how many participants we need for this kind of correlation test, we can use the power_core function from the Penguin package in Python. For example, if we expect a moderate correlation of 0.4, want 80% power, and set our significance level to 0.05, we'd need approximately 46 participants. Luckily, our dataset has a total of 500 participants. Before running the test, let's check for the assumptions. One assumption is that the variables have a linear relationship. We can generate a scatter plot with lmplot function from seaborn library in Python, plotting height on the x-axis and weight on the y-axis, and coloring by gender. If the points follow a roughly straight line without curves, linearity holds. Looking at the plots, we can see that the heights and weights are linearly related. The second assumption for running a correlation test is that both variables should be normally distributed. We can check this using the Shapiro function from scipy.stats on the height and weight columns in the vitals dataset. If the p-values are greater than 0.05, we fail to reject the null hypothesis of normality. For both the tests, we see that the p-value is more than 0.05, and therefore we can proceed with the Pearson's correlation test. To perform the correlation without considering the gender groups, we use cor function from the pingouin package with method equals to Pearson on height and weight. The output gives us the Pearson's correlation coefficient R and a p-value. Here the correlation coefficient is 0.79, indicating a strong positive linear relationship between height and weight. If we squared the correlation coefficient, we get a proportion of variance, which tells us how much of the variation in weights can be explained by the heights. In this case, 62% of the weights can be explained by their heights. To focus on just one gender group, we can subset our dataset first. Here we have isolated the males in our dataset and ran a Pearson's correlation test just like before. Lastly, we run a power analysis for the correlation test using the power_cor function from the pingouin package. We provide the correlation coefficient 0.79, sample size 500, and significance level of 0.001. This calculates the statistical power of the test. In this case, the power is 1. A power of 1 indicates a very high likelihood of detecting a true effect, supporting the reliability of our conclusion. Spearman's rank correlation is a statistical method used when the data doesn't meet the assumptions required for Pearson's correlation. It looks at how closely the rankings of the two variables match. If the data isn't normally distributed, we can use the Spearman correlation to explore relationship between the two variables, either across the whole dataset or within specific groups. This method compares the order or rank of values rather than the exact numbers. It works well with ordinal data or continuous data that doesn't follow a normal distribution. Spearman's correlation measures whether the relationship between two variables is monotonic. A monotonic increasing relationship means that one variable goes up and the other tends to go up too, though not necessarily in a straight line. A monotonic decreasing relationship means that one variable goes down as the other goes up, but again, not necessarily in a linear way. This is less strict than the Pearson's correlation test, which assumes a straight line relationship. We can use a scatter plot to check if the trend is monotonic or not. Let's say we expect a monotonous relationship between heights and weights. We want to test this across both genders. The null hypothesis is that there is no monotonic relationship between the heights and the weights. To determine the required sample size, we use the power_cor function from the pingouin package. To detect a correlation of 0.3 with a 80% power at a significance level of 0.05, we'd need 85 participants. But luckily, we have 500 participants. To run the Spearman correlation test, we use the cor function from the pingouin package specifying the method as Spearman. This calculates the correlation between the height and weight without splitting the groups. The output gives us a Spearman correlation coefficient of 0.77, which indicates a strong correlation between the heights and the weights. We can run the same test by each groups by subsetting the dataset as well. Before running the test in each group, look at the scatter plots to see whether the relationship is monotonic or linear. Sometimes the overall data may show a monotonic trend, but within each group the relationship might be linear. If so, Pearson's correlation test could give better results. To calculate the power for a Spearman's correlation test, we can use the pingouin's power_cor function. We specify the expected correlation coefficient as 0.77, sample size of 500, and the significance level alpha as 0.001. The resulting power is 1, which supports the reliability of our findings. With that, we have come to an end of this video on A/B testing in Python. Please check out my other videos on R and Python, especially the ones on linear regression. I am planning to make a dedicated video on logistic regression. So stay tuned and thank you.